Alive, yeah. That's a major accomplishment. Seriously, driving on the highways, right? Like, yeah. I think that a lot of you are in the know, but we do have a fire drill at 1:10. So class will resume after the fire drill. With that in mind, though, maybe we should just see if there are any homework questions and perhaps remind ourselves where we left off on Tuesday before we actually start doing content. So are there any questions on the homework? 2.4, number 5 and 13. Okay, so this one is number 5 with technology. This says number 5-T. Graph the function using a graphing utility with the window -1, 2, -10 to 10. Use the graph to determine if the following limits. Determine the following limits. Complete parts A through D below. Okay, so we can graph it. If we factor out the denominator, we'll see the places where that function is not defined. So we factor out an x, we've got x squared minus 1 times x. The function is not defined at 0, 1, or -1. I'll have to go back. So the reason they chose the window is just so you could see, you know, if we looked at it on this window, if we looked at this graph on this window, we might not get an accurate picture of what it is. So the window they provide is just so you can get this piece that's down here too. Because they said from x value of -1 to 2, and a y value from -10 to 10. Oops. Was it any particular part you were having issues with?
I feel like I wrote the wrong one down because I'm looking at it right now and I'm like, this is pretty easy.
Okay. So number 14 then?
Let me double check.
Can we do 12 on 2.4, please?
12 as well? Okay, let me modify this then. 12 and 14 maybe? 12 for sure. Oh, I should maybe 14.
Yeah, I think we should.
14, okay, 14 and 12. We'll go in order. So we're asked 12. Determine the following limit. Use infinity or negative infinity when appropriate, or state that it does not exist. Okay, so like we looked at that one example last class where it was a limit on cotangent, I believe. So let's think of this one the same way. So we have 1/2 times tangent, which is sine over cosine. And our limit laws say, what can we do with this 1/2? We have to leave it in there with the limit?
Take
no, we can take it out, it's a constant. So let's take that out and deal with it later. Because if it's infinity or negative infinity, it's not going to matter that we're multiplying by a half. Oh, this is, sorry, 3 pi over 2 from the left. So just hopefully you have an idea of the graph of sine and cosine, because we're going to answer these questions. As theta approaches 3 pi over 2, what does the numerator approach? So I'm gonna abbreviate. Here's our direct substitution into that limit. Is sine of 3 pi over 2 1? Does everybody agree with that? Okay. Here. Yeah. Here's sine. That's 1, negative 1. Here's pi over 2. Here's 3 pi over 2. So the numerator approaches negative 1. Denominator approaches what? So here's cosine. It's 1. Negative 1. Denominator is approaching 0. Yeah, here's 3 pi over 2. The denominator is approaching 0. What values of 0 are we approaching through? Yeah, we're approaching 3 pi from the left. So we're approaching 3 pi from, sorry, that's the right. Just kidding. Approaching 3 pi from the left. Cosine's approaching 0 through negative values. So what does that mean? Yeah, our numerator is fixed, our denominator's getting closer and closer to 0. There's no way to simplify this. You can't factor, you can't rationalize, you can't do anything else. So 1/2 tangent approaches infinity as theta approaches 3 pi over 2. Questions on that? I know it's been 5 days or so since we looked at this stuff, but again, hopefully you are kind of keeping up with the class as we go through the sections. Okay, so that's number 12. So 12 is, looks like a conceptual. I'm not sure if this has multiple parts, so we'll just take it one thing at a time.
It's not one part.
It's one part? Oh,
Yeah.
cool. So we're given this function, and we want to determine or find where all the vertical asymptotes are. And then for each value of A is where we have a vertical asymptote. So for each vertical asymptote, we want to evaluate the one-sided limit and the two-sided limit. So it's not obvious where this has an asymptote, if it even does, right? So our approach would be to do what?
Simplify.
Yeah, or see if we can simplify this, which entails factoring the numerator and factoring the denominator. Okay. Probably a good place to stop, since we're probably about to be ejected. There it goes. If you, yeah, I would take your stuff, you never know. That's just me. If you want to leave it here, feel free to leave it here. All right. So factor the numerator, factor the denominator, see if there's any factors that cancel. Those are going to be our wholes. The zeros are the factors in the denominator that remain, will be where the vertical asymptotes are. So what do we have on the bottom? Take out an x. We have an x minus 6. What about the numerator?
Call it an x as well?
Yeah, so greatest common factor is an x. And then we have this quadratic. So factors of 24 that add to get negative 10.
X minus 4, x minus 6.
X minus 4, x minus 6. All right, so see, I mean, we haven't used calculus at this point. We're using algebra to determine these a values, so that once we know those a values, then we can compute the limit. We might do one or two of these, but, well, I guess we only have to do one. Or, no, we don't, do we? That's a whole, and then that's a whole, isn't it? So that function is actually equivalent to x minus 4, except this function, the domain of this function is what? All real values except 0 and 6. Right? So when we graph this, you know, weird, hideous looking function, it's just the line x minus 4 with a hole at these two x values. So it's a line that has two holes in it. So that function has no vertical asymptotes. So I'm assuming there's a choice that says no vertical asymptotes. But if, you know, if one of them remained, let's just say like let's say x remained, then at that point we would compute the limit as x approaches 0 from the right, from the left, and then we could use these two, oops, f of x, and then we could use these two to tell us something about this limit. So that's all they were wanting there. If you did have a vertical asymptote, compute the limit on both sides of it. Because depending on what those, remember what those limits told us, kind of gave us a sense of what's happening. You know, if I approach 0 from the right and the function is positive infinity, or the limit is positive infinity, 0 from the left, and the limit's negative infinity, we get a sense, at least right here, around the asymptote and right here, what the function's doing. Yeah. So I'll just write our results here. There are no vertical asymptotes. F of x. Okay. Yeah.
Let's say, to add to that, is it okay instead of showing all that, like for test purposes, if we just simplify the fraction and then plug a positive 6 into the numerator and denominator and try that? Because that's what I did. I got 0 for both, so that's how I figured there's no asymptote there.
So you actually, so what you're saying is, if I understand correctly, you're saying that you took the function and just evaluated it at 6.
Yeah, after when you simplified it up top,
yeah.
the x out, instead of bringing it as x minus 4 by x, or yeah, by x minus 6, I just left it as x squared minus 9x plus 18 over x minus 6, and then I just plugged 6 into both, and I got 0 for the numerator and denominator. So.
Okay. Was it the same function?
Mine was slightly different numbers, except for mine was a little different for the numerator, but I guess it would still. I was wondering if that would still work.
Depends on what you had up top.
Okay.
Because if we did evaluate this function 6 over 6, then you do end up getting 0 over 0. You don't see maybe just a straight evaluation of this. You wouldn't see that this 0 over 0 actually puts you in this situation.
Oh, gotcha.
So you'd want to carry it further to see like what exactly is happening here when I get this situation. Because if we get 0 over 0, like we've seen in the sense of limits, it doesn't always mean the thing doesn't exist. So if you just evaluated and said, well, when I plug 6 into that function, it causes me to divide by 0, so I can't do anything else, that's totally incorrect. All of this is going to show you is that the function is undefined at x equals to 6, and we need to, go through this process we just did to determine what's happening there. Yeah. Any other questions on that? Other homework questions?
So why exactly is there no vertical asymptote on that function since there would be 1 and 0?
So I guess the value of x where that function's undefined at 0, that ends up dividing away too.
Oh, yeah.
Yeah, so that's, in the sense of a limit, if we were just computing the limit, if you were asked to compute the limit as x approaches 0 on this function, and it was given to you like this, we then think about what we did in like 2.3, where we said, well, when I plug this value in, it causes me to divide by 0, so let me see if I can simplify this. So then we would simplify this function in this way, and get here and say, well, as x approaches 0, what does that function approach? What is the limit as x approaches 0 on this function?
-4.
Yeah, -4. -4. Because that function is this function. Even though the function's not defined there, we approach a finite number. As x approaches a finite number, rather, y approaches a finite number, which means that we have a hole, right? If we approach a finite number, so if I were to approach, I don't know, whatever, finite number on that function and end up with positive or negative infinity, then what does that tell me about the function? A vertical asymptote. If that's my result, then I know without even looking at the graph, without even looking at what the function is, what this statement right here is telling me is that whatever f of x is, it does have a vertical asymptote at 1. Remember, that's how we defined the vertical asymptote in 2.4. We said that the definition, what a vertical asymptote is this right here. But it was more specific, or generic rather, as x approaches any finite number, the function values approach positive or negative infinity, that's automatically constituting a vertical asymptote at x equals to a. Are there any other questions? So in 2.5, where we left off, we started looking at limits at infinity, x approaches infinity or negative infinity, on polynomial functions. And we did take a slight detour and say, previous to limits, how do we determine end behavior? We looked at the leading term test, and then we sort of asked the question, well, why does the leading term test work? How come when we're talking about end behavior, how come we're allowed to just look at the leading term? And we said, because all of those lesser terms are matter significantly less as x keeps growing and growing and growing. So did anyone have any questions on any of this? In reality, you have computed limits at infinity before. In previous courses, when they said, determine the end behavior of this polynomial. You've computed a limit at infinity in your head via this chart right here. So you have already done it, it's just that we haven't put a formality to it and or the proper notation. But all we're saying here, all of this stuff is just telling us that to compute a limit at infinity on any polynomial. So let's be clear that we're just solely talking about polynomials at this point. To compute a limit at infinity on any polynomial, we need only to look at the leading term. I don't know, look sounds weird, so I'll just look at the leading term. So does everyone have what they need, or should I leave that up for a minute?
Just one.
Okay. Linear functions are also polynomials. Good news. So example, evaluate the limit at infinity on 5x to the fourth, blah, blah, blah. Just be mindful when you're asked to evaluate a limit at infinity, another way to ask this question is to determine the end behavior. So determine the end behavior is equivalent to computing a limit at infinity on whatever function you're dealing with. So some questions might say determine the end behavior, then it's up to you to compute the limit at infinity and at negative infinity. So this is where it starts to be very helpful recognizing what type of function you're actually dealing with. I mean, it's already been really helpful, but again, another reason. We're computing the limit at infinity on a polynomial function. All we need to do is look at the leading term. So what we're saying is that in the sense that x is getting larger and larger, and only because x is getting larger and larger, this limit can be evaluated just by taking the limit as x approaches infinity on the leading term, 5x to the fourth. All of the lesser terms are very insignificant when x is getting larger and larger and larger. And then if you need to, you can work with this limit symbol symbolically. In other words, what we're thinking about now is if I take 5 and multiply it by an arbitrarily large number that's raised to the fourth power, what happens? What would the answer be? Yeah, it's still positive infinity, right? Infinity raised to the fourth, that's still infinity, times 5, it's still infinity. just like we said on the previous page, we started off by asking the question, is it ever possible when x approaches infinity or negative infinity that the y values also approach infinity or negative infinity? And we said, yeah. When did that happen? On polynomial functions. So x is approaching infinity, y values, or the function is approaching infinity. So let me kind of, I'm gonna move this down. That's good. Is everybody okay with what we've done there? Are there any questions? So thinking about the graph of this function, I don't know what this graph looks like, but after computing that limit, I know one thing about it. The fact that when x approaches infinity, the y values of this function also approach infinity. So I know somewhere way out there that function is kind of ending up there in the first quadrant. What about the limit as x approaches negative infinity?
Still infinity?
Still infinity, good. Again, limit at infinity polynomial, all we need to do is compute the limit at infinity on the leading term. Then we can think about this symbolically. Again, if I take an extremely large negative number, raise that to the fourth power, what happens? You have an extremely large positive number. Extremely large positive number times 5, again, is infinity, the positive infinity. So what that tells me is, as I approach negative infinity, my function is approaching positive infinity. So I have my end behavior, you know, the arrow's pointing up, if you will. Yeah.
Just for recap, how did you get a positive infinity from 5 being multiplied by the negative infinity again?
So it's negative infinity to the fourth.
Oh, gotcha.
Yeah. And if you look back on your previous page, that totally jives with the leading term test that we wrote down. We said the leading term is 5x to the fourth. It's got an even degree and a positive coefficient. So the end behavior is behaving just like a positive 1x to the second power, right? Which these arrows are doing this.
Question, when you have a fading node come from the left, what if it's, because on the top one you just have infinity, not infinity coming from the right? Do you include both of them, or just you're just always going to do it on the right?
Well, so make sure we're clear on the notation. This means that x is approaching positive infinity, and this one's negative infinity.
So you don't have to have a plus in front of it?
No, so, and I mean, that's a good conceptual question. So, you know, the question is more along the lines of x approaching a positive infinity from the left. Would you ever see that? No, how come?
I mean, it's just going one way.
Yeah, right. So like infinity is this thing that's way out here that we can never reach, right? So there's no way to approach it from a direction, right? If we're all of this notation means when we see this is it just means what's the limit on the function as the x values get larger and larger and larger. That's really all it means. We can't approach infinity from the other direction. Like I can't approach positive infinity from the right or negative infinity from the left. I just don't see that. Was that helpful? All right. Were there any other questions? All right, so how about example 2? What will the limit as x approaches negative infinity be? negative infinity. Do y'all agree?
Yeah.
It's gonna be positive infinity.
Or, yeah, so let's look at it. Sorry, I'm just trying to get this out of the way to a more appropriate place. I think it does need to be here, just in general, as a general thing, whenever we're computing the limits at infinity. Excuse me, it's just the end behavior, so please remember that. Okay, so x approaching negative infinity on, again, another polynomial function. All we have to do is look at its leading term. So that's equivalent to computing the limit as x approaches negative infinity on negative 2x to the fifth. So we're plugging a negative infinity in for x, I guess. That's how we're thinking of it anyways. So should it be positive infinity or negative?
So it's still a negative.
Minus
You're
2.
good saying the negative too?
Oh, the negative 2, yeah, sorry. Just kidding. What should it be? Positive. Because when we raise a negative large number to the fifth power, it's still a negative large number. Times the negative 2 makes it positive. Oh, I already had that worked out. Well, it's good to see it again. Do y'all remember the show Dinosaurs? Does anybody remember that?
Oh, yeah.
That little baby that says again. All right. So again, if we think about the graph, negative 2x to the fifth minus x squared plus x, what we're saying is that as x approaches negative infinity, the y values approach positive infinity. So whatever this graph looks like, we know that over here on this end, out towards negative infinity, that the y values are up here. And flip back to the leading term test, where we have an odd degree with a negative coefficient. Our leading term test. Would tell us that this function behaves in this manner. Right. The arrow up here in the second quadrant, the other arrow down here in the fourth. So whether you remember that or not, you have done it before. Do y'all have any questions on this?
What's the importance of finding out that it's a positive infinity when it ends up being negative infinity?
Just to determine, like, well, as I approach negative infinity out here, is that arrow up here or is it down here?
So if it's a negative,
Right. So if we approach negative infinity and the limit evaluates to negative infinity, we know that when we're way out here, that the y values are doing this.
I just use the test, it's a lot easier.
Right. Yeah. So the test is a lot easier, but that's kind of old school stuff. We want to use the new school stuff. We want to use the limit. I know we know how to find vertical asymptotes, but now we have to find vertical asymptotes using limits. I know we know how to find the end behavior, but now we have to do that using limits. So a lot of the stuff you see, personally, I think it's a little bit more tedious to use limits, but everything that we've done so far really cannot be justified without the existence of a limit. So, you know, it's almost like we learn these things backwards. We learn the really easy way, and then we will learn the super technical way, what's really happening. So that's kind of where we're at. We've grown up in our math careers. Now we're, I guess, I don't know, maybe teenagers. Learning to drive a car. Probably a terrible analogy, but. Okay, so the proper definition, as f of x or as the y values become arbitrarily large, just means they keep growing in one direction or the other, never stop. Then we write this limit as x approaches infinity of f of x equals infinity. Similarly, if we approach negative infinity, we could have, the variation. I could approach infinity, the y values could approach positive or negative, and if I approach negative infinity, the y values could approach positive and negative. So really what we're getting are the arrowheads in all four quadrants with this definition is really what that's showing us. And then a recap of the leading term test showing us where the functions, they don't have arrows, but they're implicit. So those are all there. And we see that those two things summarize, as well as some other things about limits at infinity in theorem 2.6. So theorem 2.6 is dealing with limits at infinity on polynomials. So a lot of times it does matter what kind of function you're dealing with, because some things are applicable to this kind of function, whereas other things aren't applicable. The theorem deals specifically with p of x, defined there as a polynomial. And so the first statement says the limit at infinity, doesn't matter if it's positive or negative, on x to the n is infinity when that power is even. So this first statement here, visually, is just saying this right here. The second statement is now dealing with a leading coefficient, or a leading term whose degree is odd. And that second statement visually is described here with all of our odd powers. Is everybody clear on that? I think it's really important to take a graph like we already know these things, or we should already know these things, and then take a more precise statement and attach it to what we're seeing. That way it sort of solidifies what all this gibberish actually is telling us. Okay. So 1 and 2. Property number 3. As we approach positive or negative infinity, the function 1 over x to a power approaches 0. Doesn't matter what the power is, whether it's even or odd. And we've alluded to number 3 at the beginning of this section. So if I take the limit as x approaches infinity, and let's say, 10 over x to the 6th, the numerator stays fixed at 10, and the denominator gets larger and larger. And honestly, let's do this plus minus, because it doesn't matter. If the denominator gets larger and larger in either direction, the numerator is fixed, the quotient gets smaller and smaller. And this is what 3 is saying. 4, let's see, p of x.
Would you grab 3? Or is it 0 is just enough?
We could end up getting a graph of 3, but what this is saying,
It's where it's just like it's closer and closer to 0, correct?
the y values, yeah, the y values are getting closer and closer to 0. So we haven't yet fully described what we're talking about here in 3. But if I take the limit at infinity on this function, limit at infinity equals 0, then what does that say about the function 10 over x to the 6th? Just think about it this way. I'm approaching infinity. Sorry, that's not very straight. I'm approaching infinity, and the function 10 over x to the 6th is approaching 0. So I don't know, it could be approaching 0 like this, or it could be approaching 0 like this. I don't know. I just know that as I get further and further out this way, the y values get closer and closer to 0. So what is that describing?
Horizontal asymptote.
Yeah, who said that? Yeah, horizontal asymptote. So the end behavior of polynomial functions, it doesn't really have an end behavior. It has a direction it heads off in, right? But as far as the behavior towards the very end, in the sense of like a rational function like this one is, it doesn't actually level off to any specific value. When functions level off to a specific value, we call those things horizontal asymptotes. But nonetheless, as we pointed out earlier, the limit as x approaches infinity on this function, doesn't matter what function is sitting there, if you're computing a limit at infinity, you're always talking about the function's end behavior. Polynomials don't really have end behaviors. They continue off in these directions. The end behavior with rational functions, sometimes they level off, sometimes they don't. And that's what we're going to talk about next. Okay. In property, or item number 4 is telling us what? Anybody want to describe that in plain words? What number 4 is saying?
It could be positive or negative.
Yeah, the limit could be positive or negative, infinity. Any other contributions to add?
Seems like it's just contributing to what y2 are.
Yeah, that's exactly right. 4 is our leading term test. All 4 is saying that is what we wrote down here too. The very end of this page here. To compute a limit at infinity on any polynomial, we need to only look at the leading term. So if we look at item number 4, to compute a limit at infinity on p of x, which is any polynomial, the next step, all we have to do is look at the limit at infinity on this one right here. This is the leading term. Which we see right here, that's the leading term of that polynomial. The leading term of that polynomial. So it depends on the degree, like what 1 and 2 said, and it depends on the leading coefficient. So things we already knew, we're just making those statements very precise in a mathematical language. That's all we're doing there. We've virtually talked about everything on there already. Does anyone have any comments or questions on that? All right. So then, from polynomials, we'll move to rational functions. So remember, rational functions are a function that is a ratio of 2 polynomials. So if I take like 2x squared divided by x, that's a rational function. X plus 1 divided by x minus 1, rational function. Rational functions have at most one horizontal asymptote. Meaning that when we compute the limit at infinity, if it does have a horizontal asymptote, the limit at infinity and negative infinity are exactly the same for rational functions. We saw that this was not the case with polynomial functions. Specifically, if polynomial had an odd degree, where one arrow pointed up and the other pointed down, infinity and negative infinity. But rational functions, if they do have a horizontal asymptote, both limits are equivalent at infinity. And maybe if we like just sketched a graph of a rational function, like something like this, for instance. So hopefully those functions seem somewhat familiar, right? So notice whether we approach infinity or negative infinity, the function itself is getting closer and closer to 0. So to evaluate limits at infinity on a rational function, we're just going to utilize our limit laws that we saw in 2.2. And we're going to utilize limits at infinity on polynomials that we just looked at. That's really the easier way to think about these kinds of things. So here's an example. So we want to evaluate the limit. Let's say this, evaluate 1, the limit as x approaches infinity. Our function is 2x cubed plus 3x squared minus x minus 1. And all of that's over x cubed plus 5x minus 12.
There's no difference between like just saying limit as x approaches infinity versus like f of x as the limit approaches infinity, right? It's the same thing.
Yeah, so I could, this is, in this case, f of x would just take the place of all of this. The
Okay.
limit as x approaches infinity on f of x.
Okay.
Yeah. Well, the nice thing about limits at infinity is we don't have to worry about factoring anything. It's only when we approach like 1 or 6 or 0 where we had to say, well, is that function undefined at any of those places? When we compute this limit at infinity, remember the limit law says that we've got the limit of a quotient. So I can take the limit of the numerator divided by the limit of the denominator. So at least for this example, I want to work it out this way. This is equal to, just to kind of show you where it leads us. Limit of the numerator divided by the limit of the denominator. And we don't have to work all of these out this way. I'm just kind of trying to justify these limits in a way that we've seen before. So now what we're looking at individually, numerator, denominator, is the limit at infinity on a polynomial. So that's a polynomial, limit at infinity, denominator, also a polynomial, limit at infinity. So now we've already addressed how to evaluate those limits. Let me move this over. To evaluate the limit in the numerator, it's a polynomial. All I need to do is look at the leading term. So this limit up top is equivalent to the limit as x approaches infinity on just 2x cubed. Similar thing in the denominator. It's equivalent to the limit as x approaches infinity on x cubed. Now, before we actually compute the limit as x goes off to infinity, what do we know about 2x cubed divided by x cubed? Say that again?
It's the horizontal asymptote.
It's going to give us the horizontal asymptote just by the nature that we're computing the limit at infinity on a rational function. It's going to tell us whether or not it has a horizontal asymptote. That's correct. Also, what else did I hear over here? What do we know about 2x cubed over x cubed?
It's 2.
It's 2, right? And 2x cubed divided by x cubed equal 2, as long as x isn't 0. So that limit is equivalent to this limit. And so as x goes to infinity, what's our limit there? 2. The limit is equal to 2. Do y'all have any questions on that? Now, coming from previous courses, is probably one of these things where it's easier to remember it the other way, the way that you previously learned how to deal with these things. But we do need to put the limit stuff with all of it. What do we now know about this function? 2x cubed plus 3x squared minus x minus 1 over x cubed plus 5x minus 12. From that limit, what do we know about it?
As x approaches infinity, it's going to be 2.
Yeah, as x approaches infinity, the function values, the y values approach 2. So what does that mean?
Horizontal asymptotes.
Horizontal asymptote at y equals to 2. Yeah, I'll just write this out. I didn't label it as f of x, so I don't want to confuse things. So that function has a horizontal asymptote at y equals to 2. This 2. We're saying that as x gets way, way, way out here, that function levels off to a y value of 2. Sorry, keep it. Yeah, you're fine. So, I mean, it's really hard to tell. Did I graph that right?
2x squared, not 2x.
Oh, 2x cubed, yeah. Yeah. So let's go back to the. It's looking at the graph. It's hard to tell, but then when we zoom way out, it looks like the graph is really flat. So we might suspect that there is a horizontal asymptote somewhere, because as we get further and further out, the graph looks flatter. But even here, it's kind of hard to tell where that value is. Is it actually at 2 right here? Because it looks like, here we zoom in. Okay, it's still below 2, right? But not quite. Maybe we're not quite sure. And so we compute the limit. Comes out to be 2. We're probably very sure at that point. That's our horizontal asymptote. So, I don't know, way out here. And we would expect, for large values, an x value of 600 even, how close the function is to the asymptote. Still have any questions on this? And since this is a rational function, if someone asks me to compute the limit as x approaches negative infinity, I can just say it's also 2. But that's only applicable on a rational function. Okay, another example. What's the limit as x goes to infinity on 3x plus 2 over x squared minus 1? So, just by show of hands, who actually remembers when you're given a rational function, how do you find the horizontal asymptote? Who remembers that from pre-calc or algebra? Nobody? One, okay. And so, if that were the function that was given to you in a prior math course, they would say, determine the horizontal asymptote, and at which point you would say, okay, well, what's the degree of the numerator? What's the degree of the denominator? If the degree of the numerator and the denominator are equal, they are here 3, then we take leading coefficient divided by leading coefficient as the horizontal asymptote. So we went through that whole process in like algebra or pre-calc, and we said, okay, well, the leading coefficient is 2 divided by 1, which is 2. Therefore, that has a horizontal asymptote at 2. We showed that. Given a function where the degree of the denominator is larger than the degree of the numerator, what happened? I heard somebody say it. The horizontal asymptote is 0, y equals to 0. And the third condition was, what happens if the degree of the numerator is larger than the degree of the denominator? Yeah, you have no horizontal asymptote. So that's how you were remembering it prior to this course. Now, with these limits at infinity on rational functions, you don't really have to remember those criteria. Which degree is larger? What do I do in this situation or that situation? You don't have to remember that. You just have to remember how to compute this limit, because it's giving us the same information. So really, this limit is equivalent to the limit as x approaches infinity. All we have to do is look at the leading term divided by the leading term, because they're both polynomials up top and on bottom. And then, like we did with the last one, before we compute that limit, let's simplify algebraically. 3x over x squared is equivalent to 3 over x. As x gets larger and larger, what happens? 3 over x does what?
Becomes 0.
Yeah, it gets smaller and smaller. It approaches 0. The numerator is fixed. The denominator gets larger and larger. The quotient will always approach 0. So we know the function 3x plus 2 over x squared minus 1 has a horizontal asymptote at y equals to 0. Since a lot of you don't remember the degree of the numerator, degree of the denominator stuff, I think that's probably actually good, so you can practice evaluating limits at infinity and then interpreting what that tells you about the horizontal asymptote. Otherwise, we have a tendency to default back on prior knowledge. Just because we're more familiar with it, we assume that it's easier. But just because we're familiar with all of those criteria, it doesn't actually mean it's easier. We would just have a tendency to default to it because we already know it. Consequently, it's a rational function. The limit at negative infinity is also 0. So you can have plus minus infinity here, really. But I do want you to keep in mind, when we're determining in behavior, if it's not a rational function, then you have to look at limit at infinity and a limit at negative infinity. It's only with rational functions where we can look at both at the same time. Do y'all have any questions? Does anybody remember oblique asymptotes or slant asymptotes? Yeah, kind of. Yeah, so remember when you had an asymptote that was like this, your function was following it this way or this way, something like that. In the sense of a horizontal asymptote, this was not a horizontal asymptote. These limits would also show us that, because if we looked at a function like this, the limit would just end up being infinity, meaning that the function never actually levels out, which it doesn't. But the way you find those horizontal or those oblique asymptotes was you had to do long division. No. Yeah, we'll look at one of those in a moment. So the harder way, I don't know, hard's in parentheses because it's sort of relative, but the harder way is to take the highest power of x that shows up in the denominator and divide every term in the numerator and the denominator by that particular term. So divide all terms in both the numerator and denominator by the highest power of x that appears in the denominator. So I know we've already computed this, but think about the harder way as a more generic way or general method to compute these types of limits. Whichever method you find makes more sense, please use that one. I personally don't care which one you're using. So we're computing the limit at infinity. We're dividing everything by x squared, right? The highest power of x in the denominator is x squared. So we're going to take every term and divide that by x squared. Because after all, we are dividing here through by x squared minus 1. So that's the highest power of x that appears in the denominator. So we divide everything that we see in that function by that. And then we simplify this algebraically. A 3x over x squared is 3 over x. This one we're just going to leave 2 over x squared. X squared on the bottom over x squared is 1 minus, or 1 over x squared. Just simplify what we can algebraically. And then we compute the limit. X is going to infinity. What does 3 over x approach as x approaches infinity? 3 over x approaches what? 0. Yeah, we just looked at that. Numerator's fixed, denominator's getting larger and larger. So this thing is approaching 0. What's 2 over x squared approaching? Also 0. 1 is approaching 1. 1 over x squared is approaching what? 0. So this is, this is 0 plus 0. Up top over 1 minus 0, which is same result we had just by looking at leading term over leading term and then dividing, but it's a more generic process. So this process is really what's involved, if we had to compute like the limit of like exponential over another exponential, this is the process we would follow. Because exponentials don't have a leading term, right? So it's not as nice as the previous method, but in some instances it's necessary to do this way. Do y'all have any questions on that? How about this limit at infinity? What I'm trying to do is hit all of those ones that you would have saw in the pre-calculus class, just so we can connect back to them. Does anyone want to share what they got for this? Okay, so what would that limit be? Infinity? What do y'all think? Is this limit infinity? Don't worry about plugging infinities in for all of those. Just like with polynomials, right? We only looked at the leading term over the leading term, or the leading term here, leading term over leading term. So this limit is essentially the same limit as if we just looked at 3x to the 4th over 3x cubed. And we know that simplifies algebraically to x approaches infinity, x so as x approaches infinity, x approaches infinity. Which means way out there, our y values are just growing up and up and up and up. So here we have no horizontal asymptote because the y values do not approach a finite number. And so if you look at all three of those examples that we looked at, it does cover all three criteria for what was presented maybe in a pre-calculus or an algebra class. Here, the degree of the numerator is larger than the degree of the denominator, so there's no horizontal asymptote. This example, degree of the denominator was larger, horizontal asymptote at y equals to 0. And that first example, the degrees were equal. We had 2 divided by 1. So please, if you can look at these functions and know automatically where the horizontal asymptote is, you still got to work the limit out, because that's where we're at now. Is everyone clear on that? If on the exam you just said this function doesn't have a horizontal asymptote, and there is no statement regarding a limit at infinity, then you're going to lose some points. So I'll say, either evaluate this limit or determine the end behavior, or use limits to determine the horizontal asymptote, or something of that effect. Questions on any of this? you want to take a break? I don't know, the fire drill was a definite interruption, but I don't know that that was a break, so. Does a break sound okay, or do you want to keep going?
I wouldn't mind doing that.
Let's take a break. We couldn't control that fire drill, so let's continue here with this. I think I'm going to forego the process of finding an oblique asymptote. They don't show up in the homework where it says find the equation of the oblique asymptote. But just as a reminder, when the degree of the numerator is 1 more than the degree of the denominator, you can actually divide those two that polynomial by that polynomial and obtain an equation of 9 as the result of your division. And that would tell you where the oblique asymptote, or the equation of the slant asymptote, which is just a linear asymptote that's not horizontal. But in those instances where you had a slant asymptote, it wasn't a horizontal asymptote, so you said there was no horizontal asymptote, you would still get the same conclusion whether you remembered it's a slant asymptote or not, because as x approaches infinity, this thing is equivalent to this thing. And much like in the last example, what we have here is that this function actually simplifies to 2x. And as x goes to infinity, this goes to, the limit approaches infinity. Again, similar to that last example, we would say that this function has no horizontal asymptote. So I'm going to leave the rest of that blank because we're kind of short on time. Like, discuss oblique or slant asymptotes. If you want to review that, feel free. It's not going to show up on the exam. That's originally what I intended, but we're going to move on. Do y'all have any questions on limits at infinity for rational functions? Okay. So we're going to take a detour here to prepare us to look at the end behavior or the limit at infinity on other types of functions that aren't polynomial or rational. So if someone asks you what the square root of x squared is, what would you tell them? Square root of x squared is equal to x. So let's just check that. If I take the square root of my x, let's say our x is 2 squared. Does everybody agree that we would get 2? Okay, but we didn't specify what that x was, so that has to work for the square root of negative 2 squared. What do we know that to be? Equal to? It's also equal to 2, because it's 4. Square root of 4 is 2. Does that mean we're correct? The square root of x squared equal x? No, that's not a correct statement. The square root of x squared does not equal to x. Why? Well, here's an example why it doesn't. If the square root of x squared were equal to x, then this example number 2 would have to come out to be negative 2, because that's our x. This is our x, this is our x. Yeah, absolute value. So that's our counter example as to why the square root of x squared doesn't equal x. It really depends on where x is, as we saw with specifically this example right here. Oops. example number 2 shows that it does depend on where x is located. So in fact, the square root of x squared is the absolute value of x. So then this makes sense. This makes sense now because it's the absolute value of -2, which gives us 2. All right, well, why does that matter? Thinking about what we're doing, we're computing the limit, we're computing limits at infinity. So why would this matter? I'll give you a hint. What if you had a function that involved like the square root of x squared plus some other stuff? Why does that matter to know this?
Will it help with end behavior?
Yeah, it's going to help with end behavior because what this says is it matters where x is. If x is positive, then that's fine. We don't need to worry about any technical information, right? But when x is negative, like the square root of -2 squared, we do have to worry about details. And the details are, that thing has to be, we have to take the absolute value of that. So think about this example 1 here. This is kind of pertaining to functions that involve like square roots of x squared as we go off towards infinity. But example 2 is pertaining to when we go off towards negative infinity. So this is, like in context, this would matter not when we're computing the limit at infinity for this one, but when we compute the limit as x approaches negative infinity. We have to be super aware of what's happening to our values. We'll look at a few more of these. Continuing in the same vein, what would the square root of x to the 4th be? Do y'all agree it's x squared? Do we need absolute value here? No, why not? Right. No absolute value here is needed. We don't need I'll abbreviate absolute value, ABS. We don't need absolute value since the result, x squared, is always positive. If that were meant to be negative, you would see it as a negative x squared. But if I square any number, it's always positive. How about the square root of x to the 6th? What would that equal?
Which one? X cubed.
X cubed? What do y'all think? Is it x cubed?
Yeah.
So some people said yeah, some people said absolute value. We then really have to ask ourselves, just like in that x square root of x squared, is x cubed always positive for all values of x? No, x cubed is not always positive. So we need the absolute value here. X cubed is not always positive. Thus, absolute value, ABS, is needed. Sorry, I got a little sloppy there. How about the square root of x to the 8th? What does that equal? X to the 4th. Do y'all agree? X to the 4th? X to the fourth is always positive, no absolute value needed. How about the square root of x to the 10th?
Absolute value of x to the fifth.
Yeah. So if you say x to the 5th, that's wrong because x to the 5th is sometimes positive, x to the 5th is sometimes negative, so we need absolute value there. You'll see the pattern. So this is important when we look at the next example, functions like in the next example. So this function's not a polynomial, nor is it a rational function because we have the square root involved in the denominator. That's cubed. It's supposed to be cubed. There's a couple of ways to look at it, and we'll look at it both ways, but here's the graph. If we were to just assume that, okay, well, as I approach infinity and negative infinity, it's only going to have one horizontal asymptote. If it does have any, it's going to have one. That's an incorrect assumption. So here is that function. You see that as x approaches positive infinity, the function levels off or approaches 2. But as we approach negative infinity, the function approaches negative 2. So you actually have two different horizontal asymptotes coming from both in behaviors, at infinity and the other at negative infinity. Now granted, there's no way for us to know that. We're just kind of pretending that we have some sort of future sight and then we know that. But in reality, we didn't know that. So how do we come up with both of those asymptotes? It says state the in behavior of this function. And in behavior means we compute two limits. One at infinity and the other at negative infinity. That's what in behavior means, compute those two limits. We'll go through it the long way. When we come back on Thursday, we'll think of it in a bit of a shorter manner. So remember the generalized long way or the hard way to do this was to divide everything in top and bottom by the highest power of x that occurs in the denominator. So what's the highest power of x in the denominator? X to the 6th. But the problem is that we're kind of mixing operations, right? The entire denominator is the square root of, whereas the numerator is not. So x to the 6th, as long as we're underneath the radical, what happens when we divide up here? Are we going to divide through by the square root of x to the 6th? No, we're going to divide through by what? Not x cubed.
Absolute value of x.
The absolute value of x cubed. That's why it matters. So all of these are, the ones in the denominator are fine. They're under the radical. That's easy to see. The highest power is x to the 6th. But it's only when we go to mix it with the numerator that we have to worry about what we're actually doing. Oops, sorry. X to the 6th. X to the 6th. X to the 6th. Because I don't want to take everything in the numerator and divide it by the square root of x to the 6th. I mean, that's what we're doing, right? But we're going to simplify this. So I'm just going to write this out in a few steps so we maybe have a better sense of what we're doing. And we're going to remind ourselves over here that the square root of x to the 6th is actually the absolute value of x cubed. And by definition, the absolute value of x cubed is just x cubed if x is 0 or positive, but it's the negative of x cubed if x is negative. So it does absolutely matter, because since x is approaching positive infinity, we're going to use the top definition for the square root of x to the 6th. When we approach negative infinity, we're going to use the bottom definition. So we'll pick back up there